Yes. Okay. Now we can start. So what we're going to be looking into today is just an incline simulation. So as you probably know, if you put something at the top of an incline, it's going to roll off unless it has some kind of friction in between the object and the surface, or maybe it's really rigid, the surface is really rigid. So there's different factors in which you can use inclines to influence the motion of something at the top of it. But most of the time, what do you have if you put like a marble at the top of an incline? What's going to happen? It's going to roll down. So it's that simple. So if I have this kind of incline right here, okay, so basic incline. If I just put it at the top, like you just said, it's going to roll down. How can you increase the speed of the object when I put the object on here? Reduce the friction. So that's pretty hard to do, right? That means that you're going to have to redo the whole surface, or you're going to have to clean it down really well to make sure that the coefficient of friction kinetically is smaller. So that's a lot of work to do. What's something simpler that you can do with this? So the initial force that's going down on this, let's look at that real quick. So what are the forces, if I'm not pushing it, I'm just letting it roll down, what are the three main forces that we're looking at for this?
Gravity.
Gravity is one of them. So for this, gravity points straight down no matter what. Okay. What's another one that we were mentioning before? It's a resistant force. Friction. So with friction, what happens is the friction force is perpendicular to the plane, and it has to resist motion. This is the way we want motion to go, because it's going to be going down the slope. So let me try to make this a little bit better. But there we go. So that's our motion, and we can see that friction is going to be opposing it. What's one more force? You might not remember it from high school.
Force of the table of the surface on the marble.
Exactly. So that's called the normal force. So that's going to be pointing like this. So this is actually perpendicular to the surface. This is parallel to the surface, the force of friction. So this looks kind of weird, right? Because these are kind of in the same plane. They're perpendicular to each other, but this one is not. So what do you think we need to do with this force? So this is when you break it into components. So if you break something in components related to the angle it's in relation between these two, then you can make it relatable between those two and, understand equations based off them with their forces. So just to make things simple, and we won't go too in depth with it, mg on this side is going to be sine theta. You're going to just multiply it by sine theta. On the other hand, in the y direction related to the plane, it's going to be mg cosine theta. We'll go more in depth later on. If this were a course, we would go more in depth with the angles. But for now, this is just a basic understanding that the weight does need to be broken into components. Does that make sense? Okay. So you said that there would have to be a change of force, right? So if we just look at everything here, and let's eliminate this mg that's going straight down. Okay. We're looking at weight in two different directions, the normal force and the force of friction. What's the one thing that we can change? What's the one force out of all those that we can change? It would be the gravity force. So this right here, mg sine theta. So what you can change out of this is your angle or your mass. Gravity is a constant, right? 9.8 meters per second squared. You guys remember that as well? Awesome. So you're probably wondering, what angle do you need to change? This is the angle you need to change. And that's what I was trying to get to. The angle of your incline can be changed. And so that's how you can make the speed increase. And we'll see later on when we replicate the incline experiment that that's how we're going to be able to do it. So do you think increasing the angle or decreasing the angle will increase the speed at the end of the ramp? Right. Because if you imagine it decreasing, then just imagine a skier on a flat line. He's not going anywhere unless he's being pushed, right? But if you imagine a skier on almost a perfectly vertical line, he's going to be falling a lot, and that would probably not be good. So that's the main thing here. The other thing that you can kind of change is the force of friction, because you can write the force of friction in a different manner. Force of friction is equal to negative mu times the normal force. Do you know what mu stands for? Correct. So this is the coefficient of friction, and all you need to know is that it just depends on what the surface is made of. So let's say that my laptop right here is the incline. So it has its own coefficient of friction, while my notebook here has its own coefficient of friction. It's going to be sliding down at different rates with those. Does that make sense? It's just the material that you have. Smoother surfaces, they're going to have less coefficient of friction, and also if it's more rough, then it's going to have a higher coefficient of friction. Okay? So with this, another way of saying the normal force is looking at this direction, the y component of our force system. So that's why I said it was important to break components up for our force diagram. If you have the sum of the forces in the y direction, is it moving at all in the y direction here? Is it moving up and down off the ramp? No, it's not. So you can just say equals 0. So from here, then you can just say that Fn minus mg cosine theta, because that's the sum of them, but they're in opposite directions, that equals 0. What's another way of saying that? This minus this equals 0, or what?
Not sure.
So let's try to write it up. Markers are dying on me. So like I just said, Fn minus mg cosine theta equals 0. They're equal, exactly. So if they're equal, then you can just bring this over here, right? So the force of friction is also influenced by the angle and the mass. So you see how those two relate to each other? So we just want to see how fast or how much faster our object at the end of the ramp is going to be, because the force of friction, which is negative, is going to increase, but also this weight, our mg sine theta up here, which is the main force that's bringing our object down the ramp, is also increased. So there's a couple factors we need to put in here. Does this all make sense? Awesome. So the last thing I want to say is, what if we had objects, let's say that I'm going to roll this marker down this ramp, and it's just going to go off, right? It's not going to slow down for a while because it's pretty smooth. What if I did it on the rug right here? Is it going to still roll as fast, or what is it going to do? It's going to roll slower. Because why?
It's bumpy.
Exactly. The carpet has a different material. It's more bumpy. There's more ridges. And even though you can't see them, they are there. So it will be decreased. So that's pretty much it. And yeah, we can just look at how much faster the angle influences the speed of this object down the ramp. Okay? Okay. Stop. Sorry, hold on. Let's see if the computer knows how to do it. Yeah. Tap the touchpad and swipe to select stop recording. Yes.